Good morning. Before we start today's seminar, I have a few housekeeping details. Please look around and notice where the exits are located. In case of an emergency, evacuees will go down the stairs in the main lobby or any other exit that you see when you come out. Drinking fountains and the restrooms are on the I Street side of the building. And just before we begin, for those that are viewing on the internet, regarding the Q&A, we encourage you to send your emails to the address found at the bottom of the screen. It's sierram@calepa.ca.gov. We encourage you to send emails at your first opportunity, being that we will have time to air them before the end of the seminar. Dr. Williams?
Thanks, Peter. Good morning, everybody. Thank you for attending this morning's seminar titled Environmental Exposures in Early Childhood Education Environments. Our speaker today is Asa Bradman, and I'm Jeff Williams, and I was the contract manager for the majority of this study. And what I'd like to do is take just a couple minutes to place this research in context and how it fits into our research program. I'd also like to talk a little bit about the results, the findings, and how those findings are ultimately used by the Air Resources Board. Okay, so why did we fund this study? Well, I think it's important to bear in mind that this is a study looking at early childhood education environments, and that comprises children basically 5 and under. So these are the youngest children, and we know that these children are more vulnerable to the effects of air pollution. There are a few reasons for this. One, children experience higher exposures to contaminants than adults per unit body mass. Also, children are still developing immunologically and neurologically. And third, exposures can exacerbate existing conditions such as asthma, impair neurocognitive function, cause reproductive harm, particularly in the case of exposures to things like endocrine disruptors, and even increase the risk of cancer. Now, unhelpful levels of some air pollutants have been found in prior studies of California schools and homes. In fact, some of these studies have been funded by the Air Resources Board. But there still exists a data gap, and we really had very little information on what was happening in the early childhood education environments. So we needed a better understanding of exposure in daycare centers. And the results of this study really fill an important part of that data gap. Okay, so with that, I'm going to spend just a minute talking about the health findings, and I'd like to talk about the most important findings and also a little bit about how these findings are used by the Air Resources Board. The most salient finding was that most air pollutant levels in daycare centers are very similar to those in schools and homes. But one pollutant that is commonly found to be elevated in indoor environments is formaldehyde. And EC facilities were no exception. In fact, most facilities had levels of formaldehyde that exceeded health guidelines. Now, as far as particulate matter is concerned, many facilities had particulate levels, in particular PM10, that exceeded the California ambient air quality standard. Also, lead was detected in many of the facilities in the floor dust. And lead is an issue and dust is an issue because children exhibit hand-to-mouth behaviors and thereby ingest the dust. So, of course, this makes reducing these exposures very important. And ARB has already taken actions in many cases to help reduce these exposures. One of which is the air toxic control measure to reduce formaldehyde emission from composite wood products. And this regulation is expected to improve indoor air quality over the coming years. We've also put in place consumer products regulations, and there's also the California Green Building Standards Code, which will help to reduce emissions from some sources. But challenges lie ahead to reduce formaldehyde. Oh. You know, it's funny, I get going and you guys can speak up if I do something like that. It's okay. My apologies. So if you'd like, I can just recover this really quickly. Again, the air toxic control measure for formaldehyde to reduce emissions from composite wood products. And as I had mentioned, consumer products regulations in the California Green Building Standards. And where I had left off is that the challenges lie ahead to reduce formaldehyde from other indoor sources. And those are sources like carpeting, our clothing, so there are numerous sources. We've also put in place control measures to reduce particulate matter from outdoor sources, and these will continue to reduce indoor particulate levels. Also, we've provided guidance from many of these results that we use to help people understand how to further reduce their exposures. And in fact, we have a fact sheet on our website. There's a copy of it in the back. It's basically this fact sheet here that describes to people what steps they can take to reduce their exposures. In particular, taking steps like purchasing low formaldehyde emitting wood products that comply with our formaldehyde regulations, cleaning frequently to minimize levels of dust, and also using green cleaning products around the home. Okay? Now this time I don't have to advance a slide. So with that, I would like to introduce Dr. Bradman. Dr. Asa Bradman is an environmental health scientist and international expert in exposure assessment and epidemiology, focusing on pregnant women and children's exposures to toxic substances. He worked for many years with the California Department of Public Health and then co-founded the Center for Environmental Research and Children's Health in the UC Berkeley School of Public Health. He has extensive experience supervising exposure, biomonitoring, and epidemiological studies, and examining pesticides, flame retardants, VOCs, and other contaminants. He's participated on several advisory bodies at local, state, and national levels, and was appointed by Governor Schwarzenegger to the California Biomonitoring Scientific Guidance Panel. And so on that, I'd like to add a personal note. It's really been a pleasure working with Asa over the last couple years. He and Fraser Gaspar have done a tremendous amount of work, produced a final report that really went above and beyond our expectations for this contract. It's very data rich, very well written, very complete, 400 pages. I urge you all to rush out, get a copy, read it. It's, you know, New York Times bestseller on the way. Anyway, with that, I'll close my remarks, and I'd like to turn this over to Asa Bradman.
Thank you for that introduction. And I also want to thank Jeff Williams and Peggy Jenkins for their role in this project. They've put in a lot of good advice and helped deal with all the challenges that go into a contract and getting it through and getting the product out. So thank you. So you've had an introduction to the project. I also want to acknowledge some of the other contributors to this, including co-authors. You mentioned Fraser Gaspar is now a PhD student at Berkeley, and then Randy Madalena at LBL, and other people in our group at Berkeley, Rosemary Castorina, Elodie Tong Lin, and Thomas McCone. They were also very important in this project. And then the laboratory contributors as well. A lot of different labs we interface with and a lot of different analyses. So with that, just a brief overview of the presentation today. I'm going to talk very briefly about environmental concerns in childcare, and then focus mainly on the results of the study. And we'll have time for questions and afterwards. So just very quickly, childcare facilities in California are regulated by the Community Care Licensing Division. There's approximately 50,000 licensed childcare facilities in California. About 10,000 of them have a center license. That means they're in a standalone building, and they can be any number of configurations. They can be for-profit, nonprofit, religious, in schools, Head Start, et cetera. Those are distinct from the family daycares, which are much more common, and those are in homes. There's large and small. However, most kids in California, about 60% of the children in child care, are in center licensed facilities. The family daycares are much smaller, so the centers have most kids, but many children actually will cycle through a home-based facility, and then as they get older into the nursery school range, will go to a center preschool. Nationally, there's about 13 million children in child care across the country, and in California, there's more than 1 million of our children who spend time in child care. So it's an important place where our children spend a lot of time. There's also about 150,000 staff employed in child care in California, many of whom are women of childbearing age. So there's a number of potentially vulnerable populations that spend a lot of time in child care, not just young kids. One point I like to make is that in many cases, the child care or preschool environments may actually be of better quality than where the children live. In many cases, especially in low-income areas, there can be very poor housing quality. And there's a number of studies that have shown that kids in child care actually have, for example, lower lead exposure. This is an example from a house in an apartment building in Monterey County that was actually shut down, but they had extreme problems with pest infestations. So again, just to make the point that childcare is often a good place for kids to spend time. Dr. Williams reviewed some of these concepts, but why are we specifically concerned about children? They have higher exposures than adults in the same environment. And for ARB, I think one of the key issues for this is that they eat, drink, and especially breathe more than adults per unit of body weight. They breathe about twice as much air, depending on the age, than an adult. So if there's more stuff in that air, they're getting more of it into their body. They're physiologically immature. They can't metabolize compounds in the way that we can and get it out of their bodies in a way that doesn't hurt their bodies. And also, the way I like to put it, their systems aren't in place. They're just forming. And a great example here is the idea of our neural architecture, which is developing when you're a young child. And if you're kind of building a structure and you get a neurotoxic exposure, you can kind of break down that structure and won't function optimally as the child matures. So children are in many ways more vulnerable than adults. There's a number of environmental concerns that are being addressed in childcare and that have come up in the last 5 or 10 years as more concern about this environment has arisen. This is not a universal list, but just to make the point that there's a lot of areas where there's opportunities to improve environmental quality, and many of these actually deal with issues around air quality. For example, chemical hazards, cleaning, indoor air quality, pesticide use, et cetera. So there's a big role for air as kind of a key exposure pathway to children. In general, there's very little laboratory data, concrete data on exposures in childcare. There have been a few studies done nationally by EPA with HUD, but there's been no environmental monitoring in California. We did this survey with the California Department of Pesticide Regulation. In fact, Belinda Messenger here, I worked on that with her. And this is some of the only data on pesticide use in California. But again, these are all survey data, and there's been no environmental monitoring really of any kind in child care facilities in California before this project. So that led to this study, which has already been introduced. But to summarize the objectives here, one, the goal was to complete measurements of environmental contaminants in 40 ECE facilities. ECE means early care and education, and it's often used interchangeably with child care. We ended up looking at 20 facilities in Alameda County and 20 in Monterey County. The goal here was to get kind of a cross-section of geographic and areas and also different land use environments. We used questionnaires and inspections, and then we took that information and tried to estimate potential health risks to prioritize both research follow-up and perhaps policy implications. Again, we recruited in those 2 counties. To recruit participants, we used the California Department of Social Services database for center licenses, and we used that then to assign those addresses to specific zip codes. And then we tried to randomly select facilities from each zip code. The address information for family daycare is not publicly available. So for that, we worked with local referral agencies who do maintain confidential databases of local family license facilities. And then we actually provided them with recruitment letters, which they mailed for us confidentially. We're able to recruit participants through that method. There was also a certain amount of word of mouth. Recruitment, especially for family daycares, was challenging. Just to give a visual of the areas we looked at, the one on your left is Alameda County, the one on the right is Monterey County. We basically took several zip codes in each county that had different characteristics in terms of level of urbanness, the land use, and then kind of aggregated them together where they had roughly equal numbers of childcare facilities per geographic unit, and then selected from that. But you can see we had pretty wide coverage of each county. The questionnaires and inspections were ones that we adapted from existing inspection and environmental assessment tools that have been developed previously for schools and homes. We've done a lot of work like this in the Salinas Valley, and we basically adapted it to the preschool environment to complete an environmental assessment, things like mold, mildew, pest infestations. We also asked about behaviors related to cleaning, maintenance of equipment, and then also education and attitudes of the staff towards environmental concerns, hoping that could be used later on for education purposes. We also took things like the GPS coordinates so we could link that, for example, to traffic data. And then we conducted a fairly detailed inventory of chemicals on site, both cleaning and pesticides and things like that. Okay. Okay, can everyone hear okay? Thanks. So, just to summarize again, we collected air and dust samples from 40 childcare facilities. We measured a lot of things. In the air, we measured several different types of particles, including real-time measurements of particulate matter, gravimetric measures of particulate matter, PM10 and PM2.5 and ultrafine particles, and then a range of chemicals, including phthalates, VOCs, carbonyls, meaning things like formaldehyde, pesticides, flame retardants, PFCs, perfluorinated compounds, and metals. Some of these things, of course, are not very volatile. Metals were measured only in dust. We had some problems with the laboratory methods for PFCs, and also those are, again, not very volatile, so the levels, we really couldn't get levels that were high enough to measure with our methods. But most everything here was measured in both air and dust. And then, of course, on the other side, things like VOCs and carbonyls don't show up in dust, so that was just in air. But again, a wide variety of chemicals and particles were measured. Other data collected: temperature, carbon dioxide, which we used for air exchange rates, occupancy. This was somebody, Fraser spent all day in these facilities recording how many people came in, left, whether there was a door open or closed, a window open or closed. We found that things like air exchange rates would vary dramatically at different parts of the day. For example, in the afternoon, there might be a long period when it's hot and windows are open, or parents are constantly coming in and out and changing the characteristics of the building. So there were a lot of challenges. I want to review some of these just so you have an understanding of what it took to get this in the field, and also those of you who might want to do this kind of work in the future. One was access. In the beginning of the study, there was a lot of resistance we encountered about outside people coming into a facility who had no record of being in child care facilities before. Concerns about equipment, child safety. Noise was a big issue. When we first put our equipment together, it was overwhelming, and there was no way we could put these facilities inside a classroom. And then some other measurement challenges. Our first idea was, well, we could just build a little kiddie corral and put all the kids in there, and that would work. But it didn't work, so instead, we built a little kiddie corral around our sampling equipment. And that was effective in keeping the kids out and was also monitored by our staff. I put this little fingerprint up there because one child care center director who declined our participation suggested that we all go out and get fingerprint and criminal background checks that are required, regularly for people who work around children. So all our staff and myself did that, and then we provided those materials with the consent forms during recruitment, and that dramatically improved our recruitment. The noise issue, initially we thought we could solve it just by giving earmuffs to all the kids, but that proved a little cumbersome. So I don't have a picture here, but we developed we used a stainless steel box, put a single rotovane pump in that, insulated it with fiberglass, and then put on a muffler, a HEPA filter, and a carbon filter to make sure we weren't putting materials into the room from the pump, and we were able to actually bring the noise from this pump down to the sound of basically an aquarium pump. And then we linked that to a manifold on the right with a series of flow meters so we could actually calibrate the airflow for each individual sampler with the flow meter. And that also worked well because we had a visual sight on all the airflows. And for example, if something became clogged or the power went out, we would immediately know that there was a change. So that was a good system and really took care of most of the challenges we had. In terms of technical challenges, in the beginning, we had a lot of problems in our first couple facilities estimating air exchange rates. As I mentioned, there was wildly variable numbers with doors opening and closing at different times of day. We also found that child care directors were resistant to the idea of, for example, using some sort of tracer or some standard method to enhance the air with a tracer and then look at the decay to calculate air exchange rates. We also have the issue that even an air exchange rate calculation for a given unit of time might not be reasonable for the entire day. So what we ended up doing is monitoring carbon dioxide through the whole day, but once or twice during the day, usually just once. When the kids were outside the room, we introduced medical grade carbon dioxide into the room to bring it up to about 2,000 or 2,500 parts per million. And then we measure the decay of that over the time frame. So that allows us a fairly controlled time to look at the air exchange rate. And then we also modeled the air exchange rates over the entire period. We made sure that the measured air exchange rate during the CO2 enhancement period was consistent with the model for other times of day. And so we were able to ultimately calculate an average air exchange rate for each facility during the day and also identify periods when they were higher. You can see here on this lower line, the black line at the bottom measures changes in occupancy. And you can see that during the day, sometimes there were 10 people in this facility and sometimes none. On air exchange rate 3 on the side there, you'll see that a bunch of doors were open at the end of the day and the air exchange rate, I'm sorry, in this case the doors were closed and the air exchange rates went down for a short period. So this turned out to be an effective way to address this challenge. Another problem we had, and this slide is a little hard to see, but you see these big peaks from the chromatogram. You can see there's a big broad peak and a big high one there. We were finding these unknown peaks in our sampling tubes, and it turned out when we compared these to the NIST spectral libraries that they were alcohols. And we then went and did a little study in our office where we took some hand sanitizer and put it out on the table, and it turned out that these problems were due to these enormous flooding of the sample tube with alcohols from hand sanitizers. And you can see here on this graph on the right, on this graph, I'm sorry, on your left, you'll see a big peak going down, whereas on the line above it, there's no similar symmetrical peak, and that's an example where this alcohol created this flood of materials on the sampling tube. So we ended up ultimately sampling for VOCs on 2 separate tubes, one using 10X as a sorbent, and the other separate tube using a carbotrap as a sorbent, and that we were able to separate out the alcohols from the total VOC samples. For formaldehydes, we used a silica gel cartridge, is pretty standard aldehyde sampler. Semi-volatile chemicals, things like phthalates and pesticides, we used pre-cleaned, solvent-clean polyurethane foam cartridges. For ultrafine particles, we used a condensation particle counter from DSI. Particulate matter, I mentioned earlier, we did a real-time sample with dust tracks and gravimetric sampling and weighing. And then finally, all the dust collections were done by the HVS3 vacuum, which basically is a method to collect floor dust that's very effective, used by EPA. So now to move on to some of the study findings. As I mentioned, we had a fairly broad geographic area. We also recruited a number of different building types, including a number of single-family detached homes, either homes that were being lived in as family daycare facilities or had been converted to center facilities, schools, including both traditional classrooms and portable classrooms, office buildings, excuse me, and a few churches. So a wide range of building types. In general, the child care facilities were in good physical condition. There were minimal problems with mold, mildew, rotting wood, et cetera, and the heating, ventilation, air conditioning systems were well maintained. About 93% were compliant with the California Building Code minimum of about 0.35 air changes per hour. The flip side, of course, there is about 7% were not compliant, and there might be some opportunities here to increase ventilation. Pests were common. This is something we found in our survey. Most of the facilities, probably 90-100%, reported some problems with pests, mostly ants or invertebrates. About 60% reported using pesticides, and about 45% had been using sprays, very similar to the results we found for the 650 we surveyed across the state. And these issues are typical of other California facilities, nothing unusual here that we found in our study. There were quite a few chemicals that were stored in these child care facilities, often in closets adjacent to rooms where children spent time. We were able to identify 135 chemical ingredients with CAS registration numbers, including things in paints, solvents, a lot of cleaners, for example. Stainless steel cleaners included things like petroleum distillates and other products. In addition to that, there were 32 different pesticide active ingredients stored or used on site. So quite an array of materials that are could potentially result in airborne contaminants. And again, just to underscore though, storage at a site doesn't necessarily imply exposure. To summarize some of the information we found on volatile organic compounds, we quantified 40 VOCs, and there was a very strong trend of higher levels inside. You'll see here, I don't think my pointer here works, but you'll see here the average ratio of indoor to outdoor VOC levels was 37. So levels are much higher inside, although there was a broad range from about 1 to benzene to very high for D-limonene, 1600, which is a common component of cleaners. Benzene, of course, often comes from evaporative releases from fuels, so there's probably a big outside contribution to that. Definitely, before I step there, just to look at the figure here, this I think provides a good visual of the difference in levels between indoor and outdoor levels. You'll see on the left here, the darker box plot here for formaldehyde had a median of just below 20 and levels up to 40, whereas if you look at the levels for the outdoor side, outdoor levels on the right, there was basically none. So just to underscore that a lot of these materials have indoor sources and are higher inside. Finally, if you look at the correlation between air exchange rates, ventilation, and formaldehyde, it was -6. So very good evidence that higher ventilation can reduce the levels indoors and that the indoor sources are important. Is that? Oh, okay, there it is. Great, thanks. I'll keep that out there. In absolute terms, in terms of the highest materials with the highest concentrations, they were both D-limonene and also this siloxane. Both these compounds are associated with cleaning and personal care products. Siloxanes are more in personal care products. So there's definitely a relationship here between VOCs inside and especially cleaning materials. We found some relationships, for example, with nearby traffic metrics. So, for example, there was a correlation with hexene, benzene, and ethylbenzene for the outdoor measurements with the intensity of nearby traffic, although the correlations were weaker indoors. So there are some unique sources for these VOCs indoors, and there's probably some concentration from outdoor sources like traffic as well. VOCs are, kind of mentioned earlier, the health effects that Jeff Williams mentioned, they kind of span the range of potential health effects. There's a lot of different kinds of volatile organic compounds. Some are respiratory irritants, some are potentially neurotoxic, others are carcinogenic, they can be hematotoxic or other endpoints. So there's kind of a broad range of chemicals, focusing on the ones that tended to rise above some of the health benchmarks we looked at. Formaldehyde is a respiratory irritant. It's considered a carcinogen under Prop 65 and has a standard in California for a reference exposure level. The median in our study was about 17 or 18 micrograms per cubic meter, and this compares to the OEHA 8-hour and chronic RELs of 9. So our median level was about twice the standard, and altogether about 88% of the facilities had levels of formaldehyde sampled over an 8-hour period that were higher than the 8-hour REL. So some potential concerns there. None of the measurements exceeded the acute REL, so they weren't over the top in terms of that standard. Acetaldehyde, another carbonyl, was not higher than the California reference exposure level, but did exceed the EPA reference concentration, which is calculated similar to the California REL with a few different more assumptions. But in about 30% of facilities, this carbonyl was also over the EPA standard. Just to give some perspective on the levels of these compared to other studies, and also these now are means. We just go back and forth between means and medians. But the top row of childcare facilities was the findings in this study, and then this compares to some other more recent studies. One in 2009, the new California home study, you can see where the levels there were much higher than the levels that we measured in childcare facilities. However, the levels we measured in our childcare facilities were very similar to studies, a decade ago in portable classrooms and traditional classrooms. I should mention too that the new home study obviously focused on new homes, and the overall levels in California homes are probably somewhat lower. So these levels are, again, they're similar to some other studies that have been done over the last decade, but it does suggest there's more room for improvement in getting those levels down. We also compared a number of the VOC exposures that had classifications or had been reviewed by OEHA and had a defined no significant risk level. The no significant risk level is essentially an intake rate or an exposure rate that is set at what would be considered under Prop 65 an acceptable cancer risk, which is about 1 in 100,000. So if you plug in cancer risk of 1 in 100,000 and plug in potency there, you can do some algebra and come up with the NSRL. We use the OEHA guidelines, which have developed recommendations to compute child-specific no significant risk levels. And that basically includes accounting for the lower body weight of children and also the age-specific sensitivity. And they've defined specific age specific factors. So we did some calculations and compared the potential exposures to our child-specific NSRL, and in addition to formaldehyde, which is not surprising, several other compounds also had potential exposures that exceeded the child-specific NSRL. So these also are of potential concern. Chloroform could be related to disinfection products, which are bleach products are commonly used in childcare for sanitizing. And then the benzene and ethylbenzene are potentially indoor sources from, for example, cooking, and also outdoor samples from sources from traffic. I want to make the point here that we sampled over 1 day. So we don't have a sense of the long-term variability in these levels, but it points to some concerns that should be looked at more carefully. Another issue we came up with was that there were many peaks in our chromatogram from the machines measuring the compounds that we were not among the 40 that we had included calibration points for, and were basically unknown, and also exceeded many other VOC levels that we had seen in other studies. So just to provide a visual on this, if you look at the red columns here versus the green was the mass of VOCs that we quantified in individual samples, and the red was the proportion or the additional contribution of total mass from unknown VOCs. So if you look, for example, over on your right, you'll see that in this case, we just labeled these by letter here, facility M and N. Most of the VOC in those facilities was unknown. So there's a lot of other stuff out there. In fact, in that case, probably 90% of the total mass of VOC carbon compounds were not quantified there. So we wanted to look at this more carefully, and we took those chromatograms and then compared them to the NIST spectral library, like we did with the alcohols earlier. And this is kind of a central repository of retention times and peak characteristic data maintained by the National Institute of Science and Technology, or Science and Testing. They've changed their name a couple times. And if we had an 80% or greater level of certainty in a match, we tentatively identified that peak as that chemical. And then we quantified the levels by comparing them basically to a generic calibration model based on toluene. Overall, we were able to identify 130 additional VOCs that were likely present in our facilities. And in fact, when we took the subset of 40 that we did quantify and ran them through this toluene prediction model, we were able to show that we had about a correlation of about 0.87 or close to 0.9 between our mass estimate based on the toluene model and our mass estimate based on the actual calibrations for that subset of 40 where we had calibrations. So overall, we think we have a pretty good estimate of the amount of these other substances that were in the air. This list is not meant to be read. The point of this slide is that there's a long list of chemicals, 130 additional chemicals that were likely present that warrant some more attention and more research to quantify them and better understand what they are, what the levels are, and what are the potential health impacts. I'm going to shift over now to flame retardants. A big concern in California because of the TB 117 from the Bureau of Furnishings. We know that's under review right now. In general, levels of the flame retardants in air were relatively low. Many of these compounds have relatively low vapor pressures, so that's not surprising. We did tend to find higher levels indoors compared to outdoors, which underscores that indoor sources are probably more important, could be associated with some volatilization or perhaps resuspension of contaminated dust particles. So, but they were commonly present. In addition to the PBDE, the polybrominated diphenyl ether flame retardants, we also found some of the organophosphate flame retardants like chlorinated tris, a carcinogen. Some of the tris compounds are listed as carcinogens, and also Firemaster 550. And these have been used as substitutes for the PBDEs in California as the penta mixture of the PBDEs was phased out. There's a bunch of numbers up here on some of the levels in dust, and I just want to make some points here. In general, when you look at the concentrations, the median concentrations of just starting with the PBDE flame retardants, or BDE is usually the way they're abbreviated. These levels are actually lower than median levels in other recent studies of California homes. And I think that's related to the frequent cleaning that goes on in most child care facilities. But I put down the maximum there just to underscore that at the upper end, the levels are comparable to the high levels we see across California in many homes. So there's a big range overall. I think the cleaning reduces levels, but there are potentially high exposures. And then I don't really have many comparisons for the chlorinated tris in purple and the Firemaster 550 compounds in blue, but this just underscores that these are present and may be increasing recently as a substitute for the PBDEs in furniture. It'll be interesting to see down the road whether the changes in laws in California might reduce chemical flame retardant exposures. Another point of interest in the dust, PBDE 209, which is has been used, it's actually still being used, and I think it's just, there's some negotiations right now to try to take this off the market, but was the dominant congener in dust. These other compounds down here in the green and blue, or maybe it looks purple up there, those are the classic penta mixture, whereas 209 was used more in electronics, and that 209 congener seems to really dominate the materials in dust. So, and maybe an important, a more important exposure, relative to the other compounds, exposures to this may be higher. The brominated flame retardants are potential endocrine disruptors and are neurotoxic. And it looks like that the exposures, at least to very young children, based on the default assumptions by the EPA Child Specific Exposure Factor Handbook, would result in exposures that exceed a reference dose for children under a year old. So these levels are potentially of concern as well. We measured phthalates, relatively commonly found in both the air and dust. The levels in the air were not terribly high. They were generally below a microgram per meter. But again, the outdoor levels were mostly below detection limits, underscoring that indoor environments are the source of this materials. And again, there's probably some volatilization going on here or resuspension of contaminated dust particles. There was also fairly moderate, not high, but not necessarily weak correlations between levels in indoor air and dust contamination inside, underscoring that probably the dust as a route of a repository of materials that can contaminate the air. Phthalates are developmental toxins. They're potential respiratory irritants and endocrine disruptors. But for those of the compounds that did have health guidelines or health benchmarks, the exposures did not exceed those. We looked at pesticides as well. We looked at 2 organophosphate pesticides, chlorpyrifos and diazinon. They have a history of residential and commercial use that ended in about 2004, and now they're solely used in agriculture. We also looked at pyrethroid insecticides, a common, in the last 10 years, a very common substitute for organophosphates. Now, actually, nicotinal pesticides are increasingly replacing pyrethroids. Piperonal butoxide is a common synergist used in pyrethroids, and then we also looked at dactyl, an herbicide that we've commonly found in the Salinas Valley in Monterey County. I mentioned earlier there were over 30, there were not over, but there were 32 active ingredients, different pesticide active ingredients stored or used at many facilities. Probably the most common material we found is the pyrethroid pesticides, particularly cis and trans permethrin. That's frequently detected at the highest levels in dust and was also commonly present in air. The organophosphates were also frequently detected in air and dust in both counties, even though in Alameda County there's almost no use of these materials agriculturally. So there's probably some long-term residues of these materials that have stuck around inside from uses that went on, over a decade ago. Dactyl, which is this herbicide, it's used solely in agriculture and historically as well, and had much higher levels in dust and air in agricultural areas. So suggesting that there is some pesticide exposures that may be based on local land use and local pesticide use in agriculture. But interestingly, the organophosphate pesticide levels in the ag areas were not higher than the non-ag areas. Now these compounds, the OPs, tend to be a little less stable and break down. And again, there's also good cleaning indoors, and that might be helping to remove some of the materials too. Relative to dactyl, the OPs are definitely less persistent. So that might help explain the differences between those two. There were, again, moderate correlations between indoor air levels and pesticide dust concentrations, suggesting that if we can reduce indoor pesticides, for example, if there were fewer pyrethroids in the dust, we could probably reduce air levels as well. And just a reminder, pyrethroids and OP pesticides in particular are neurotoxic. That's the main mechanism for killing insects. But all the exposure estimates that we computed were below risk benchmarks. The next set of compounds we looked at were perfluorinated compounds. These are potential carcinogens. They're actually currently under review right now by the U.S. National Toxicology Program and also the OEHA here in California. I mentioned that we weren't able to measure these in air. They were commonly present in dust. About 50% of the samples had PFOS and PFOS and PFOA, the most common perfluorinated compounds, although the estimated exposures could not be compared to any health-based benchmark. So these compounds really haven't gone through a full toxicological review, but exposures are fairly ubiquitous. They have relatively low vapor pressures, so they may not be a big factor in air. We also, Dr. Williams mentioned earlier that we looked at lead in dust. Overall, the levels were relatively low. You can see the medium here is about 36. There was one facility in a very old house that had levels up around 800, which were a little high. The next level below that was in the 200s. And in general, almost all the facilities had levels that were 200 parts per billion or lower, which is lower than current standards for soil that children play in. I wouldn't expect high exposures from these dust levels, but the material is certainly ubiquitous. USEPA doesn't have any benchmark or standard for lead exposure because the assumption is that there's no safe level exposure. So I should mention here that all the results for the study were returned to participants, and the home with this relatively high level of lead was provided with information on how to reduce exposures. So moving away from chemicals now and looking at some of the particulate matter, I mentioned earlier we looked at ultrafine particles and coarser particles. The ultrafine particles were particles in air that are generally larger than 6 nanometers, or a billionth of a meter. And then we also looked at the standard particulate matter metrics for PM10 and PM2.5, i.e. Particles less than 10 microns or particles less than 2.5 microns, or a millionth of a meter. And particulate matter, I'm sure as many of you know, is a respiratory irritant and can also affect other body systems. So the levels of 2.5 and PM10, I have both indoor and outdoor here. Interestingly, if you look at the levels of PM2.5 for indoor and outdoor, they're almost identical, really suggesting that the indoor sources are not huge, at least for these, and not enhancing what may be coming in from outside air. If you look at the indoor and outdoor for PM10, the indoor levels are significantly higher. This may be related to specific indoor sources, maybe cooking. There's also the potential here for the kind of pig pen effect of kind of a cloud of higher levels around people. So, but kind of an interesting difference here. If you compare these to the US EPA and CARB standards, I think the PM10 stands out most significantly in about just under half of the facilities had levels that exceeded the 24-hour standard for PM10. I want to emphasize here that our monitoring was over 8 hours, so you can't make a direct comparison with the 24-hour standard, but this is definitely a place where exposures may be contributing to total time in an environment that could exceed the state standard and might be something worth looking at in more detail. Again, this is a visual of the difference between indoor and outdoor. Again, for the PM2.5, you can see here the ratio is 1, and basically indicating little difference and probably less contribution from the indoor environment. Whereas again, you can see the higher ratio here for the indoor-outdoor for PM10. You can see all the dots on the one-to-one line there are weighted towards the indoor side. The ultrafine particles turned out to be very interesting. If you look at the median levels, especially say here for indoor and outdoor, they're kind of characteristic of other urban or environments or other settled environments. But if you see here, if you look up at the 75th and 95th percentiles, the levels in the indoor samples are much higher than the levels in the outdoor samples. And if you look at the graph on the lower right here, these can be a little bit hard to read, both with the color and the concept here, but this is a cumulative distribution graph. And you'll see for the indoor line, which are the lighter dots on the right, at about the 60th percentile, or in other words, in the upper range, they diverge from the tendency of levels for the outdoor, and they're much higher. And again, that's also, you can see that in the numbers at the 95th percentile with 70,000 indoor and 42,000 outdoor. And we realized that the key determinant driving these changes were cooking events inside. For example, if you look at these data comparing number 18 and number 19 in our study, these two peaks on the right for number 19 were levels increased by up to 1,000-fold, up to almost 600,000 particles. That those were also timed when there was cooking going on, both to heat up lunch or snacks or soup or that sort of thing. And it was also done in facilities, it was a home-based facility, where there was no range hood or any ventilation around the stove. So we know that using a hood is good when you cook, and here's a very concrete example. And there's a lot of, I think, work to be done about what these exposures mean for health impacts. But in the meantime, there's things we can do to reduce those exposures. So just to summarize, this is one of the first studies to perform environmental sampling in ECE facilities in California. And most of the compounds we looked at have never been sampled in any other studies in the country. In general, the facilities were in good condition. Child care providers were interested in what we were doing and concerned about the quality environment. The contaminant levels were similar to other indoor environments. Most exposures were below health-based standards, but I want to emphasize here also when they were available. The majority of chemicals we looked at don't have a health benchmark that we can compare results to. The highest levels of VOCs in indoor air were related to cleaning agents or personal care products. But some others, like formaldehyde, consistently exceeded the OEHA reference exposure levels. Also, again, several VOCs exceeded child-specific, no significant risk levels that we computed based on Prop 65 guidelines. So there's some potential issues there. Lots of chemicals that we didn't measure but are likely present that really should be followed up on. And again, this issue with ultrafine particles going very high when gas stoves were used. I'm going to quickly go through this because I just covered the particulates, but wanted to move on to the recommendations before we open up for questions. One, I think kind of the general finding here is that there's exposures going on here, and as an academic, I have to say additional research is needed to look at contaminants in ECE child care facilities to better understand it. In particular, I think we need to do more work to quantify these previously unknown VOCs, to both quantify the levels and also, in this next recommendation, to complete our evaluation of the potential health impacts of these chemical exposures, especially for those that don't have formal health-based benchmarks. In other words, I think we need to go back in the literature and see what is available and see if we need to prioritize some of these compounds for a more formal state review or other review to develop an exposure benchmark. More research is definitely needed to assess the health impacts of ultrafine particles exposures, especially the big gyrations we saw in some of these facilities, which could impact respiratory function in the kids. In the meantime, I think there's lots of things we can do to encourage steps to reduce exposures to compounds. Both in the short term, they're definitely needed to address exposures related to compounds that exceed health-based benchmarks, like formaldehyde, purchasing wood products that meet the current state standard, and maybe something for ARB to consider is whether additional regulatory actions on formaldehyde are warranted. And in addition to reducing exposures to these ones that are exceeding a benchmark, I think there's real opportunity here to reach out to healthcare providers and professional groups that work with them to increase awareness of indoor air quality and adapt inexpensive ways to improve indoor environments. For example, the use of range hoods to reduce ultrafine particles, which again, there's no benchmark for it, but we know it's probably not good. And that will also have secondary benefits of reducing things like formaldehyde from cooking emissions and other sources. So I want to thank our funders, thank the Air Resources Board for this project, and also other supporters of our research center at Berkeley that include the National Institutes of Environmental Health Sciences, the US EPA, and also a lot of work we've done with the California Department of Pesticide Regulation. Also a list here, I think it's useful, additional resources on environmental quality in childcare that could be helpful both to providers or others who are just interested in this general area. So that completes my presentation. I think we're actually right on time, so this would be a good time to open it up for discussion and question.
Yes, I was interested in the model that you used for estimating the ventilation rates at the beginning of your presentation.
Right.
And I was wondering how detailed is that model? Does it include the number of windows and the size of the windows and doors and whether there's a chimney or not a chimney and other kinds of ventilation mechanisms?
To some extent, yes. Although there's actually a graduate student who wants to do a little more work with that data. But we collected a lot of specific information about the room in terms of the size, the volume, whether there were doors, to interior parts of the building, like a hallway, or whether there were doors to the exterior, and then whether they were open or closed, that sort of thing. The model, though, basically was kind of a brute force method to look at the concentration levels and look for periods when there were changes in the curve of either increasing or decreasing, relate that to sources of CO2, basically the number of people in the room. We had both child-specific and adult-specific emission rates of CO2, and then see if we can essentially just be able to predict a model that matches the line. So we didn't incorporate mathematically for example, the area of a door that was open. So it was more of a brute force, can we get the numbers to match up? But actually we're talking about, is there some way to use the information we have, which is more detailed than most studies, to actually improve that model. The fact that we found a very strong negative correlation between the air exchange rates and the formaldehyde levels and other VOCs kind of just reassured me that we had a good measure of ventilation compared to higher ventilation meant lower levels. So I think the numbers are meaningful. Question?
Thank you. My name is Jessie Schnell. I'm with DTSC. I don't think there's been a lot of biomonitoring done of that age group. I'm not sure, actually. You could answer that question for me. But the second part of my question is, how feasible is it to do biomonitoring of children in daycare centers?
I mean, in general, there haven't been studies that have targeted, biomonitoring measurements of kids in daycare to try to relate that to exposures that occurred in daycare. There are, a few studies around the state, including ours in the Salinas Valley, and we've collected biomonitoring samples from kids as young as 6 months, and now the kids are 12 years old. So it is possible to do. The NHANES data, which is kind of the US reference data, National Health and Nutrition Examination Survey data, their studies only go down to age 6. Their youngest age group is 6 to 11. So there's not good national reference data, but there's other researchers like our group that have done studies with young children. I've actually been thinking of trying to develop some proposals to work with some child care facilities to look at, for example, indoor air quality and changes in air function or exhaled nitric oxide as a measure of inflammation. And we're trying to actually see if we can get some funding to do studies like that, and whether, for example, if there was an intervention at a child care center, we can get those VOC levels or particle numbers down and therefore have a measurable improvement in the environment that we can relate to an outcome in the child. But there's challenges with that, and also both with access and also with confidentiality, and the consenting process gets challenging because you have the child care facility, but then you have all the parents involved, and it's doable, but there's challenges there. And also, of course, some of the things we measured in the environment can't be measured in biological samples. So.
Thank you, Dr. Bradman. Is this on? Yes.
Yeah.
Very nice presentation. And I know you've spent a good portion of your career looking at pesticides and children's exposures to pesticides and migrant workers. I'm wondering, are you seeing a decrease in like indoor levels or people's exposures to pesticides? Have you seen that in the data as time goes on, or are we holding level?
Right. Well, that's an interesting question because we've been working in the Salinas Valley now for, well, almost 14, 15 years. And we have actually done different kinds of sampling at different time points. And when we look at, for example, levels of chlorpyrifos over time, they do seem to be declining. And there's some other studies nationally that have shown that since they don't call it a ban, but since home use of diazinon and chlorpyrifos was the registration was changed and that was eliminated, the exposure levels have gone down. Overall in the country and in California, organophosphate pesticide use has also gone down. So there's change in the mix. The Salinas Valley organophosphate use has been fairly constant because of some particular insects that have required use of these compounds, particularly in lettuce. And so there is a trend more recently of declining levels, but the ag use has been fairly stable over the years. So it's hard to know, what trends are due to, bigger statewide trends and what might not be occurring locally. But. I'm going to read these out to you. Okay.